Hello, everyone. Welcome to the HPL seminar, which is the last one for this academic term. I'm very pleased to introduce our speaker, Michael Esposito. Mike started his undergraduate in 2015 here at the University of Calgary in kinesiology, where he had worked on validating inertial measurements units, or IMU, to estimate stride length in running. Right after he received a Bachelor of Science degree in 2018, he started master's course here at the same university in biomedical engineering under the supervision of Dr. Darren Stefanishin. During his master's, Mike primarily worked on how midsole cushioning stiffness in a shoe affects on Achilles tendon stretching during running, and Mike is going to talk about it soon. Last year, he achieved a master's degree and started PhD course early this year under the same supervisor. Since then, he's been trying to understand how external modification to shoes can influence internal mechanisms of the musculoskeletal system in a body, and how these internal mechanisms would relate to running performance. When I asked Mike if there is anything interesting or fun fact about himself, he talked about a main reason for having a beard. He said he has it so he doesn't have to shave. Today, Mike will be talking about his master's work entitled as Effects of Midsole Cushioning Stiffness on Achilles Tendon Stretching During Running. Whenever you're ready.
Thanks, Songwon. So running is a popular physical activity with millions of people participating, and running dates back centuries with competitions such as the modern Olympics showcasing running events like the marathon since 1896. However, research on running footwear in a systematic and scientific manner did not begin until the late 1970s. Footwear properties can alter athletic performance, an example being the Nike Vaporfly 4% shoe. This was used in the Nike Breaking 2 documentary, and it's shown here in the picture on the right. Some properties that have been modified include mass, bending stiffness, comfort, and midsole material properties. Looking at these modifications in more detail and how they relate to performance, we're starting with mass. When 100 grams is added to a shoe, research has shown that performance decreases by about 1%. Increasing the longitudinal bending stiffness has a mean energy savings of around 1%. And improved cushioning of the midsole has shown improvements in performance of up to 4.2%. Research has also shown that combining these modifications can further increase performance, such as the Nike Vaporfly, combining a stiff carbon fiber plate and a compliant resilient midsole. Since midsole material with improved cushioning has shown the greatest improvements on its own, it's the focus of my presentation and my research. Previous research has shown that footwear with a different midsole stiffness and energy return properties can improve performance. An example of mechanical properties of such shoes are shown here in the figure taken from Warburt's and coworkers. So on this figure, it's force on the y-axis, deformation on the x-axis. And each of these loops is the compression of each shoe. So for the solid figure, the control shoe, the slope of this line is how we determine the stiffness of the shoe, and the area in between the curve is the energy lost by the midsole. And that is for both shoes. So we can see that the control shoe had a stiffer midsole and had greater energy loss as compared to this soft shoe. And from this study, the soft shoe increased performance by just over 1%. There are several studies that have shown similar results with shoes with improved cushioning, improving performance. And from these studies, there's an average improvement of about 2.33% in performance. And based on predictions, improvements of this magnitude could reduce the current world record marathon by 108 seconds, which will put the record time under the 2-hour mark. There are multiple studies that show that cushioning stiffness can improve performance, and they use the cost of cushioning hypothesis to explain. The cost of cushioning hypothesis states that external cushioning of the shoe may reduce the need for muscles for cushioning, reducing the metabolic cost, and would explain the performance differences observed. But although there are multiple studies showing changes in midsole properties and how they can improve running economy, research has shown that the influence in cushioning on performance to be athlete specific. Studies find no group differences between the shoes, but found individual differences in running economy. An example is shown in the top right figure, with some participants having differences of up to 2%. For this study, the participants ran on 2 days in both shoe conditions. Looking at the bottom figure first, it is a similar force deformation curve that we've shown before, with the solid line being a viscous shoe and the dotted line being an elastic shoe. And we can see that the shoes differed in both stiffness and energy return properties as well. The top figure is the oxygen consumption results of the 20 participants, and it shows a fairly individual response. The black shaded bars indicate the participants who performed better in the viscous shoes on both days, while the gray shaded bars represent the participants that performed better in the elastic shoe on both days, while the white bars are the subjects who had different results between the days. And further looking into this study, even though the viscous shoe had a greater amount of energy lost in the midsole, some individuals still performed better in the viscous condition despite the greater energy loss from the midsole, a result that the authors say was counterintuitive and not expected. And these results highlight that the cost of cushioning as well as energy return from the midsole may not fully explain the performance improvements seen, and there may be other internal mechanisms responsible. There's a general belief that changes in cushioning stiffness influences the functioning of the musculoskeletal system, and there are many speculations of a mechanism linking cushioning properties to better running performance. However, further investigation of these speculations is required as there's no conclusive evidence of such mechanism. What we do know is that the Achilles tendon has a significant role in the task of running. When running, elastic energy is thought to be stored within the muscle tendon unit and is used to support and propel the body forward during running. The storage and release of this elastic energy is thought to be important in maintaining a low energy cost of running by reducing the work required from the muscles. And further, research has shown that individuals with a greater energy storage capacity of the Achilles tendon had better running performance compared to others with lower energy storage capacity. It's known that the plantar flexors are the largest contributor to mechanical work during running, and with this significant role in running, it's reasonable to believe that there's a possibility that the Achilles tendon mechanics may be influenced by footwear cushioning and may be a part of the mechanism responsible for the increase in performance previously observed. So it's speculated that with the addition of a more compliant cushioning, a lower heel position would occur during running, and this lower heel position would allow for a greater extension of the Achilles tendon and a greater energy storage and return of the tendon. This greater energy storage and return from the tendon could result in a decreased work demand from the main plantar flexor muscles. And since they are the largest contributors in mechanical work, it's reasonable to believe that the overall result would be a reduced oxygen consumption, which would be an improved running performance. So the purpose of the study is to determine if changes in footwear midsole stiffness can elicit changes in Achilles tendon stretch, in an attempt to determine a mechanism behind running economy improvements previously observed with these differences in cushioning properties. It was hypothesized that the footwear condition with better running economy for an individual will have greater Achilles tendon stretch, suggesting greater energy storage and return of the Achilles tendon during running. So for the study, there was 14 participants recruited, and all participants were able to run 10 kilometers in under 40 minutes and were injury-free for 3 months prior to testing. 2 footwear conditions were used, a stiff and a compliant shoe. The stiff shoe had a midsole made of ethylene vinyl acetate, and the compliant shoe was made of an expanded thermoplastic polyurethane pellets, commercially known as Boost. Even though there are only minor differences in mass, the shoes were matched in mass by evenly distributing lead weights near the center of mass of the stiff shoe to eliminate any potential confounding effect of mass. In the top right, we have a force deformation curve for each of the shoes. From mechanical testing, midsole stiffness and energy loss were calculated. The footwear conditions had a 23% difference in stiffness and a 36% difference in the energy loss of the midsole. These two shoes were chosen since previous research has used footwear with similar differences in stiffness and observed a running economy differences in running economy of 1% on average between footwear conditions. So testing was completed during 2 sessions. The objective of session 1 was to measure the Achilles tendon moment arm. So participants laid prone with their knee at 180 degrees, straight legged with their ankle at a 90-degree position in a dynamometer, shown here in the picture. The participants were fitted with an ultrasound probe, and the probe was positioned to measure the movement of the myotendinous junction of the left medial gastroc. So to determine the moment arm of the Achilles tendon, the ankle was passively positioned into 30 degrees plantar flexion. The ankle was then passively rotated at 5 degrees per second to the neutral position. So first 3 repetitions were done and they served as conditioning trials. And on the 4th trial, the ultrasound images were recorded. The second session was a treadmill running session. So first, the ultrasound was placed in the same location as the first session, and the participant was fitted with an oxygen consumption mask. The session began with an incremental running test on an instrumented treadmill to determine a submaximal running speed. The test started at running at 2.46 meters per second, and this increased by 0.2 meters per second every 2 minutes. And during this, oxygen data was collected and used to estimate when the participant was at their lactate threshold. When the lactate threshold was reached, the test was stopped. The speed used for testing was 1 level before the test was stopped. And this running speed allows for participants to run at different running speeds, but run at a similar relative intensity. The incremental test also allowed the participant to warm up before the test runs. So following the test, the participants were fitted with retroreflective markers, and a schematic of this is shown up on the figure on the right, with the gray markers representing the tracking markers, and the blue markers are the anatomical markers. Participants ran for 6 minutes in each speed on the instrumented treadmill, and during the final 2 minutes of the run, kinematic, kinetic, metabolic, and ultrasound data were collected. So I was going to go through an ultrasound image to get everybody on the same page of what it looks like and what we are seeing here. So here is an ultrasound image of the left medial gastroc myotendinous junction. So to orient everyone, the top of the image is the skin, the left being the proximal side and right being distal. We secured a copper wire to the participant, and that's visible in the image. And this is used to ensure that the ultrasound probe does not move during the tile. The triangle section on the left side of the image is the medial gastrocnemius. The light gray line above this triangle is a superficial aponeurosis, and the similar line below is the deep aponeurosis. The thicker light gray or white line spanning the right side of the image is the Achilles tendon, and the part where the aponeurosis and the tendon meet is the myotendinous junction. Tracking the location of this will allow us to estimate the stretch of the Achilles tendon. So from session 1, the Achilles tendon moment arm is calculated using the tendon excursion method. So very briefly, the myotendinous junction location is found before the movement begins, and this position is marked. And then once the rotation is complete, as we can see, the myotendinous junction moves across the right side of the screen. We find the myotendinous junction place again, and that position is marked. And the distance between the 2 points is then divided by the range of rotation in radians, and that is the Achilles tendon moment arm. The moment arm is then adjusted to account for differences in values obtained from the tendon excursion method and the center of rotation method, which uses MRI images to calculate the moment arm. And this was based on data from previous studies that have done this. So since there's no gold standard for moment arm measurement, but it has been shown that the tendon excursion method results in a smaller moment arm estimate on average of about 15 millimeters compared to the center of rotation method. So from session 2, movement of the Achilles tendon can be calculated. First, we find the movement of the Achilles tendon at the ankle, and that's calculated as the Achilles tendon moment arm multiplied by the tan of the peak dorsiflexion angle during stance, with a little schematic shown on the right. We then find movement of the myotendinous junction, and that was calculated as the distance between the most proximal point position of the MTJ and the wire position. And both measurements were calculated for 30 steps and then average. From these two measurements, we can calculate pseudo stretch. The variable was termed pseudo-stretch since the true stretch of the tendon cannot be determined, and it was used to find differences between conditions. Then the difference in pseudo-stretch was then calculated and used as this estimation of the difference in stretch between conditions. As related to performance, energy cost of running was used as a measurement of performance and was calculated from the metabolic data from this equation shown. So in this equation, we have the energy expenditure, which is in kilocalories per minute, and that's timed by a constant to convert it to kilojoules. It is then times by a constant that converts it from meters into kilometers. The speed that each individual ran at in meters per minute, and then times by their body mass. And this gives us a unit of kilojoules per kilogram per kilometer. The energy cost of running was used, as has been shown, to be more sensitive and a more appropriate measure. So a lower energy cost of running would indicate a better running performance. So then the differences in performance were calculated and used in the form of percent difference. Then a Pearson correlation analysis was performed to assess the existence of a linear relationship between these differences in performance and the differences in the pseudo-stretch measurements. So here are the correlation results. On the vertical axis, we have the difference in performance in percent. So the positive values indicate a better performance in the stiff condition. On the horizontal axis is the difference in pseudo-stretch, and that's in millimeters, with positive values indicating greater stretch in the stiff condition. So the results from this analysis showed a moderate positive correlation between the difference in pseudo-stretch and the difference in performance, and this was statistically significant. So 12 of the participants had a greater pseudo-stretch and better performance in the same footwear condition, and the 2 participants down here in the bottom right quadrant did not have the greater stretch and performance in the same footwear condition. The dotted black line is the trend line of the data, and as you can see that it does not go directly through 0, and it's a little bit shifted down towards, if you had 0 pseudo stretch, that you would have about 0.8% increase in performance in the compliant shoe. And this is believed to be thought due to the difference in energy return of the midsole, the differences in energy return of the midsole of the 2 shoes. So these results suggest that the cost of cushioning hypothesis may not fully explain the performance results, along with the energy return of the midsole, since this would suggest that all participants would have had their best performance in the compliant footwear conditions due to the mechanical properties of that midsole. So in the top right graph is the figure that I showed in the introduction of the subject specific response, and in the bottom is the differences in performance of the subjects from this study. And as you can see that they do seem to have a similar trend where not everyone was better in one shoe, and that they seem to be a little bit subject specific. Again, for the bottom graph, positive results mean better performance in the stiff shoe, with negative results, better performance in the compliant shoe. So this isn't to say that the cushioning wasn't involved, along with the energy return, but this theory may not fully explain the performance improvements observed, suggesting that there may be other internal mechanisms responsible for these movements. So unfortunately, from this data set, the absolute stretch of the tendon cannot be determined, and the energy stored and returned from the Achilles tendon is unknown. Previous studies have estimated the energy returned from the Achilles tendon. Estimates from Fletcher and McIntosh were used since the participants had a similar height and weight and ran at a similar speed. The estimate was 42 joules of energy returned from that study, which would equate to an approximate stretch of 22.3 millimeters. Exploring 3 values for differences in stretch, we used 0.1 millimeter, which was the smallest difference in pseudo stretch from the study, 1.4 millimeters, which was the absolute average of pseudo stretch from the study, and 5.7 millimeters, which was the greatest difference in pseudo stretch from the study. These increases in stretch would equate to 42.2, 47.4, and 66.2 joules returned. When compared to the original 42 joules, the differences range from 0.4 to 24.2 joules and averaging 5.4 joules difference in energy return. Estimates of the mechanical energy were calculated as 140 joules per step using mechanical power estimates from previous research. With this, the difference in energy return being 5.4 joules, this is 3.9% of the total mechanical energy required. Energy returns of this magnitude would be relevant and could cause the improved performance observed. And these results suggest that the energy return from the Achilles could be a valid mechanism for improving performance due to these changes in footwear. Also, it's possible that the estimations of Achilles tendon stretch were overestimated, since other previous studies have shown a smaller tendon stretch. Assuming that the stretch of 22.3 millimeters is overestimated by 50%, doing the same calculations as above, the energy return percentage of the total mechanical energy becomes 2.6%. This is lower than the 3.9, but does not change the interpretation that the energy return from the Achilles tendon would still be significant. So there were some differences I noticed between the participants that performed better in the compliant shoe and the participants that performed better in the stiff shoe. So here's the correlation graph, again, just as a refresher. So there are 9 participants who performed better in the compliant condition, and this is shown in the bottom half of the graph. And there are 5 participants that performed better in the stiff condition, shown in this top half of the graph. So in the present study, foot strike pattern was not controlled for, but interestingly, 7 of the 9 participants who performed better in the compliant condition were rear foot strikers, and 4 of the 5 who performed better in the stiff condition were mid to forefoot strikers. Strike shape was determined based on the ankle angle at foot contact, with rear foot strikers having a dorsiflex position at initial contact, and midfoot and forefoot having a plantar flex position. So it's been shown that foot strike pattern alone does not influence performance, but it may be that runners with a certain foot strike pattern combined with certain midsole cushioning properties allow for an increased Achilles tendon stretch, which could have caused the improved performance. Further, the average mass of the participants performing better in the compliant condition was greater than the mass in the stiff condition by about just under 4 kilograms. So the greater mass on the compliant midsole may cause the deformation of the midsole, allowing for greater energy return from the midsole joint side and potentially increasing the stretch of the tendon as well, which may allow for this performance improvement seen too. So although the results of the present study suggest that the energy return from the Achilles tendon may be a valid mechanism, the possibility of other mechanisms cannot be discounted. The stretch of the Achilles tendon may result in changes of the function of the triceps surae. If the length change of the muscle tendon unit during a stride is taken up by the stretching of the Achilles tendon, this will allow for less shortening of muscle fascicles and a slower shortening of velocity. Less shortening of the muscle fascicles allows for optimization of muscle activation and the force length, force velocity properties. And it is believed that the optimization of these relationships could also result in a reduced metabolic cost. However, more research is required to determine that. So there are a few limitations to this study. Absolute tendon stretch was unable to be calculated, and the energy returned from the tendon can only be estimated. In this study, the difference in tendon movement between conditions was calculated, and it's believed that this difference would be similar to the difference in stretch between conditions. Also, the ultrasound probe may have been slightly obtrusive to the runner, which may translate to an atypical running pattern. This being said, it's believed that the ultrasound probe design, since the scanning surface is parallel to the cord, that the effect would be minimal. So in the future studies, we should definitely measure absolute and Achilles tendon stretch to calculate energy return values of the tendon. Also, measurements of the tendon and muscle combined should be captured to see how they work together. And finally, combinations of footwear modifications should be tested to see if similar mechanisms are the cause for performance improvements observed. To summarize, there's a positive moderate correlation between the difference in performance and the difference in tendon stretch between footwear conditions. This difference in energy returned by the tendon was large enough to cause the improvements in performance, improvements to performance. The results of this study suggest that the energy returned by the Achilles tendon may be a valid mechanism of improved performance. And these findings lead the way for future research to further understand the mechanisms behind these improved performance, and which is what I'd like to continue my research throughout my PhD on. And understanding how these footwear modifications affect internal mechanisms could have large ramifications on potential strategies for assisting and supporting locomotion. With that, I'd like to thank my supervisor, Darren's Definition, along with everybody, current and past members of this definition group. And that is the end of my talk, but I just thought, since this was about my master's work, I thought it was only appropriate to include a quick video. As for context, on the first day of my master's, I shaved my face with the razor down to the skin and did not shave for the entire 2 years and 4 months. And then I took this video. What have I done? Thank you.
Thank you, Michael. If I would like to kindly encourage everyone to turn on your camera if you feel okay with it, so we see each other during the discussion and question and answer period. Thanks for doing it. So if you have any questions for our speaker, please use the icon raise hand button. You can find it if you go reaction icon at the bottom of your Zoom screen. If the button is not there, or you're using different version of Zoom, or if your microphone is not working, please also feel free to send me a message via Zoom chat, then I'll call on you when it's your turn. Now I'll open the seminar to the question. Yes, Brent, please go ahead.
Thanks, Mike. So the rear foot strikers, you have some evidence that suggests that the rear foot strikers are able to take advantage of this extra cushioning, which may which may lead to increased Achilles tendon stretch and allow them to take advantage of some energy storage. Have you thought about why the opposite is true for the forefoot strikers? Why, and can it be explained by the same mechanism? So I guess my question is, why might forefoot strikers get improved Achilles tendon stretch in a stiff shoe?
To be honest, I'm not entirely sure. I don't know is the quick, easy answer. I'm not sure how that works. I don't know.
You don't want to take a guess or speculate or anything?
Right now, like, it's puzzled me as much. I think it makes more sense why the rear foot strikers go, but I don't have any insight onto why the forefoot strikers and why the stiff midsole, if it plays any role, is why it's helping.
Okay, I'm not satisfied by your answer, but
Fair enough.
I'll let you go.
Yes, I see Art, you have a question for Mike?
I sort of have to just make up a question because I saw Brent was asking a question, or I thought he was just going to say something that I would disagree with, so I just raised my hand to disagree. But it turns out he was just asking a pure question, so I don't have anything to disagree with. Okay, I'll ask a question, which is, your stiff and compliant shoes, I noticed that they differed both in stiffness and in energy return. So they had different hysteresis values.
Yep.
And so I wonder, do you think it's one or the other? So is this a matter of literal stiffness versus compliance, or is it a matter of hysteresis? And then also, when people talk about cushioning, what are they talking about? Are they referring to one of stiffness or hysteresis, or are they referring to both? Or yeah, it's just I'm not sure what people mean when they say cushioning.
Okay. For the first question, yeah, I guess they do probably play a role together, the energy loss and the stiffness, or the hysteresis and the stiffness. In an ideal world, I would have had shoes that only differed in stiffness, but that was not the case. As for the second part of that question, as to what does cushioning mean, I think compliance as well as I think they're all looped or grouped together for a lack of, not always stiffness, but I feel like when people talk about cushioning, it relates to the energy return properties.
I see. And then is it typical that it's, or is it assumed that when you have higher stiffness, you also have higher hysteresis, or the opposite, or, what's the relationship?
Yeah. I wouldn't say it's assumed. From lots of from research I've seen, usually the less stiff, I haven't seen a stiffer shoe with less hysteresis when compared to a less stiff shoe, if that makes sense.
Okay, so stiffness usually, well, hysteresis usually increases with stiffness is the idea? Is that what you're
Yes.
saying?
That's what I've seen, yes.
Okay, and then, so does it matter which material it is?
Yes, the material will change the hysteresis properties.
I see. Okay, great, thank you.
Kun, please go ahead.
Hey, I apologize. I missed a small bit of the talk, so if you said it in the small bit, I apologize. But so you are correlating performance with the energy return in the Achilles tendon. Okay, but if the hypothesis is that energy storage and return is important, basically, then you could also consider adding up the energy storage and return that occurs in the Achilles tendon with the one in the shoe. Because also this is related to Art's point, in the more compliant shoe, there's not only different hysteresis, but there's also more energy stored and returned if you go to the same force level, right?
Mm-hmm.
So do you think you would get a better correlation with performance if you added up those contributions? So you looked at the total energy stored and returned in both the Achilles tendon and the shoe.
Yeah, possibly. That makes sense to see if, and that could deal with the fact that they have differences in this energy storage. The midsoles have differences. So yeah, no, I didn't do that, but yeah, that's a good idea. And that I'm not entirely sure how it would have changed the relationship, or if it would change the relationship, but there may be a better correlation.
But yeah, it's hard to foresee what happens. I don't know. Yeah.
Mike, actually, I also have a question for you. So I know you mentioned in the limitation parts that you didn't measure the whole length of the Achilles tendon for your study, but also still curious about how you measured it in your study. So you tracked the muscle tendon junction using the ultrasound machine, and that muscle was gastrocnemius, you said?
Yep.
So wouldn't it still the part of the aponeurosis, not the actual like tendon, so that the properties could be a little different from the Achilles tendon itself? And then I'm just curious if that would somehow affect to your results in your study.
I guess, yes, there's possibilities that the aponeurosis properties may be slightly different than the tendon. I guess we're just trying to go for total stretch of the entire tendon, which would have been the ideal goal. I'm not entirely sure how that would affect or change it, if any.
Thank you. I see Arash, you have also a question for Mike.
Yeah. Hey, Mike. So about this probe that you used in this study, as far as I remember, it was really difficult to do plantar flexion with the probe on. Do you have any thoughts about how this could have changed the running pattern in general?
Yeah, so yeah, the probe is, and it's right on the medial gastroc there, and it could be obtrusive. I think it, if put on properly in the correct positioning, it shouldn't cramp the person too much. And I know later in the studies that lots of people said that it was fine. but if it did affect it super drastically, I know that within subject design, it wouldn't, or like it was on the same for both shoes. Yes.
Thank you.
Siska, please go ahead.
Yeah, thank you. I was wondering, when you're talking about your future directions, how you'd measure absolute tendon strain.
Yeah, so part of that would be using motion capture in combination with the ultrasound and just markers positioned appropriately. If you were to put one marker on the calcaneus, or have a measurement of where the calcaneus is in space, and then have markers on the probe as well to know where the probe is in space, and then you would be able to determine where the calcaneus is in space to where the probe is and get that tendon length, and then use the ultrasound measurements to get the extra or the added bit of the ultrasound and use that as your entire tendon length. And then using estimates people use from Comey's study back in the early 90s of as toe off would be the tendon slack length, and then everything on or greater than that would be when the tendon is stretched.
Okay, thank you.
Mike, I think I might have missed in the beginning of your talk, but could you also just explain once more why you chose, or why would you be interested in midsole in the shoes and related to running performance? And would there be any other shoe parts, like a part in the shoes that you can modify further so that you can we can get performance improved?
I chose the midsole material properties as alone as any individual feature or piece showed to have the greatest improvement in performance by itself. I know there's been research done here by Sasha Chigoya showing that changing the longitudinal bending stiffness of a shoe can have influences on the muscle gastroc, fascicle shortening velocity as well.
Thank you. I see, Rob, you have a question for Mike.
Yeah, Mike, I have to admit, I'm always a little bit concerned about attributing a great deal to the elastic recoil in the Achilles tendon. But let me ask, first of all, when you put the ultrasound probe on the leg, what was the muscle doing? Was the muscle active? Was it trying to simulate a run, or was it totally passive?
The individual is just standing when I put it on, so it was like not actively being flexed, but just standing and like essentially in neutral position.
Yeah, because some of the stretch that occurs in the Achilles tendon, some of it's imposed when you land, and some of that stretch is imposed by the muscle fibers. So the muscle fibers are putting some of the stretch in. Mm-hmm. But when the Achilles tendon recoils, some of that shortening of the Achilles tendon is associated not with moving the skeleton, but with yielding. It can be associated with yielding of the muscle fibers. So you're basically letting go the force that's holding it from the muscle fibers. So as to how much energy would be returned elastically to the whole system, I think is always, to me, in doubt, because if you basically letting go the muscle fibers, then you know you're not returning that into the moving the skeleton. But there is an example that you may have knowledge of. In Edmonton with amputees, they had people running with just a beautiful curved spring. And if the hypothesis is that elastic return of energy in, let's say, the Achilles tendon contributes to increased efficiency, would that not be the perfect model of a perfect spring returning energy into the system? In which case, do you know if those studies out of Edmonton returned really super efficient running? Are we better off not having fancier shoes, but amputating our lower limb and putting a mechanical spring there?
I'm not aware of those studies, but that'd be something to look into to see, yeah, if the idea of the mechanism is even worth exploring. I know it, I think, yeah.
Sorry, I interrupted you.
No, I was just gonna say, in theory, it seems to make sense to me, but in theory and practice don't always line up.
Because on the other side, I'm sure it's been done, but I haven't looked at it. The rear foot strike and forefoot strike, I would imagine forefoot strike, if you had energy return in elastic recoil of the Achilles tendon, that forefoot strike would give you a much better, a significant difference to rear foot strike. But you didn't really see that, you said, I think.
I didn't look too deeply into the differences in the forefoot strike to see or to find any differences. It was just something interesting I noticed. But I just found it interesting that the people that perform better in that stiff shoe seem to be forefoot strikers, which I just thought was interesting.
Was it by, I forget the numbers, was it by much percent? Was it?
Yeah, 4 out of the 5 were. Oh,
Right.
or so are you talking about the difference in
Efficiency? Yeah.
Yeah, I think the average for in this stiff shoe was about 1.5%, I believe, increase.
Right. Right. Okay. Thank you, Mike.
Andy, please go ahead.
Hi, Mike. Sorry, having a few technical difficulties with the old camera today. I was wondering, in the plot that you're showing us, and correct me if I'm wrong here, but I believe it was a relative difference or relative performance that you're kind of showing between the two shoe conditions. I was wondering if you had correlated anything against, an absolute performance measure. So off the top of my head, maybe the speed that people were running at when you tested them at threshold or got them to threshold, etc.
No, I haven't looked at anything in relative to like different speeds or whatever. Just sorry, in terms of absolute, I've only done the relative difference.
Okay. It'd be interesting to see if it still holds.
Yeah, I don't know.
Cool, thanks.
I see Brent, you have a questions for Mike?
Andy Pohl was that outlying subject on your graph there, wasn't he?
Yes.
So the one that had the real large improvement in performance?
Real large improvement in stretch.
So what's up with him? Why does he run different than the rest?
I'm not entirely sure why he seems to have this difference in stretch. When I first saw that number, and it seems to be much larger than everybody else, I just thought I made a mistake in like the measuring of it, but I've gone back and done it multiple times and it seems to be correct. He also did have that subject did have the greatest tendon movement as well. The myotendinous junction movement, it did move the most too, as well as the greatest difference between the conditions, which from a kinematics point of view or anything like that, he doesn't run any differently. So I don't know why.
Did you look at moments and work at the ankle?
I know from between the groups of like compliant and stiff, there were no differences, but on this individual level, no, I don't know.
Yeah, because the moments are typically going to be higher in the forefoot strikers.
Yeah, I didn't look at them in between, between anything else, just the two groups of compliant and stiff.
Okay, all right, thanks.
Art, please go ahead.
This is a more general question, but it looked like your energetics results, you typically showed like a couple percent change for quite a few people. And I'm just wondering, does that mean that any serious runner should just have themselves tested? They say they should have their VO2 measured for a bunch of different shoes. It could be varying the midsole stiffness or other things. But it seems like that's such a big difference that it's well worth it for serious runners to get tested and then have a shoe selected based on that.
Yeah, that would make sense to me. You would think everyone has different running styles, and I know looking at, for example, the data from Hocamera and all that did the Vaporfly testing, and like on average they had 4%, but there are some people that were on the lower side of that range, and who knows if there's a different shoe that would make them perform better than the Vaporfly, for example. So I think for a high level, that could be worth it.
Yeah, I mean, even 1% for a high level, that's a huge improvement. And so just think about how much money they're being paid in sponsorship. So that gives an idea of how much it's worth to get an improvement. So
Yeah.
I feel like 1% is really valuable.
Yes, for sure, I agree.
I see Arash, you have a question for Mike?
So whenever I'm using this Cosmed, I'm always worried about this this range that can be meaningful in terms of milliliters. So you had a 1.5% increase in energy cost, right?
Mm-hmm.
And what that number translate in milliliters, and is it way larger than the smallest difference that you can capture with Cosmed?
The percent difference, if you do the percent difference between the VO2 values in terms of milliliters per kilogram per minute and using the energy cost of running, they're fairly similar.
Yeah. So what was the speed? I'm assuming it should be around like 45-50 milliliter. So 1% of that would be like half a milliliter.
Yeah, roughly about that. Yeah.
That number is a bit too small. I'm not entirely sure how much can be captured with the Cosmed.
Yeah, no, that's true.
But I'm assuming it should be.
Okay,
Yeah.
Can I cut in? I do think that all of these VO2 measurements are noisy, but I feel like the solution to that is just test and retest. So yeah, I don't think it's as convenient as go into the lab for a few hours and then you have your answer. But it's just a matter of how many times you retest that you can get down to whatever precision you want.
Mm-hmm.
Yeah, I was going to say in the ideal world, it would be interesting to bring these people in more than one time to see if on like within a week, do they perform better in the same shoe? And then a month or a few months later, do they still perform better in this same shoe?
Mm-hmm. And then another interesting thing about your results that 4-foot runners can benefit from stiffer shoes. As far as I know, there are a few elite runners on up the top of my head, like Zersane Tedese or Eliud Kipchoge or Kenenisa Bekele, that at the beginning of their career, they were running mostly on their mid to rear foot, and later on, after all these years, they're running mostly on their forefoot. And I'm assuming that the track shoes are stiffer than their training shoes. That might have been caused them to shift towards that, but probably just an idea.
No, yeah, that's interesting. Yeah, that could be true. That maybe, yeah, I don't know if it's true if the stiffness of the midsole can be better utilized with strike pattern.
Thank you.
Walter, yeah, you want to try your microphone working?
Can you hear me? Yeah.
Yes.
Oh, good. Yeah. Yeah. I got rid of my headphones, and so I hope this would work. Yeah. I want to bring up the same thing that has been discussed already, is kind of the reliability of O2 measurements on the treadmill. And, you know, having been a runner and being tested literally in a 10-year period, being tested like probably about 100 times, you know, there's, at least in my case, there was easily a difference of 1 milliliter per kilogram per minute, you know, from one day to the next when I was in a training camp. And so that would be about 1.5 or 2%. So I would fully agree with Art that you know, half a milliliter per kilogram per minute, you would have to do multiple measurements to really feel comfortable about that. The other thing that I wanted to bring up quickly is, you know, you talk about, you know, you often talked about performance, but you really measure, you know, oxygen uptake and convert it into kilocalories. Is that performance, or in other words, for a 10K runner like you used, is oxygen uptake the limiting factor for performance?
No, probably not. This was just used as like a measurement of their performance. I wouldn't necessarily, it wouldn't fully dictate their performance as a total if you look at it in terms of like time to finish kind of thing. There are other limiting factors. And I think with the 6-minute run, it's just, I think oxygen consumption is the best use of that 6-minute run, and compared to making someone run like a full 10K and get their time and see how their time changes.
Yeah, and I think that's really, and I think that's the right answer, because I'm exactly the same age as Marcus Riffel, who was second at the Olympic Games in 1984, and he was always very, very jealous that a cyclist called Beat Brooy, who was a fabulous climber, had a much higher oxygen uptake capacity than him, but obviously in a running race would have had absolutely no chance against him. So I think you know, oxygen uptake obviously in long distance running is very important, but I think it's dangerous to translate those changes into performance. And I think Roger Cram and other people have also shown that, you know, a 4% difference in oxygen uptake capacity in the vaporfly does not really translate into a 4% increase in performance. And
yeah,
so you have to be a bit careful about that. The other thing that I had is, you know, you made an interesting comment about, you know, when you had more stretch being taken up by the Achilles tendon, then maybe you could stay at a more optimal muscle length. Did I understand that correctly?
Yeah, the more that if the Achilles tendon length was doing more of the length change of the total muscle unit, then the muscle fibers wouldn't have to stretch as much or change as much and stay at a more isometric, quote unquote, or longer.
Yeah, because it's just one of the things that I've always bring up and have brought up with other people is that people have said that, you know, that when you keep your fascicle lengths equal, but your tendon elongates and then shortens, then you have an isometric contraction that's more efficient than if the had a rigid tendon and your fascicle elongated and then shortened. But of course, if your fascicle elongated, then in the eccentric phase, that would be more efficient than keeping it isometric. And then when it shortened, you'd be less isometric. And some people have suggested that keeping it isometric might not necessarily actually save you energy compared to if you did the eccentric and concentric with the fascicle.
Yeah, that's something that would be interesting to look at and see if we can test, like to do ultrasound on both the tendon as well as the muscle fascicles at the same time. I know the area is not so big that it might be a lot harder in practice than theory, but it could be interesting.
The other thing also seems to be that people seem to suggest, since you talked about the triceps sura and the medial gastrocnemius in humans, that the longest muscle length seems to be the strongest. So the medial gastroc seems to be primarily working on the ascending limb of the force-length relationship. So maybe it would be good to have a very stiff Achilles tendon that would force your fascicles into very long lengths because you're inherently stronger there, and that might actually be an advantage as well. I'm not sure. The last thing, you're talking. Rob was bringing up the amputee, and amputee running, of course, is always very interesting because a few years back, Oscar Pistorius, double amputee that most of you probably know, was allowed to run at the World Championships and Olympic Games with the regular runners because the idea was that he did not inherently have an advantage. And right now, a few years later, there's a case, and court of arbitration going on about an American runner, a double amputee, same situation as Pistorius, and so his appeal to run with regular runners was now twice rejected because the idea was that it actually provides an advantage. So I love to follow that discussion. Is it or is it not an advantage? Would a spring actually be for your lower limb be a better thing than your actual lower limb with all the muscles that you have and so on? So I think the jury might be out, but Art or Benno or Rob might want to chirp in here. Or of course you, Mike, if you have an opinion on it.
Yeah, I think the opportunity to artery or make a spring or blade to be optimized, I think you do have the opportunity to be more efficient than the human body. I think it's definitely possible. Whether they've gotten to that stage yet, or whether they've maximized it to be as good as it gets, I think it's definitely possible. I wouldn't say it's out of reach to be more efficient than the human body with some sort of blade or.
But it must have been measured. Someone must have done that.
Oh yeah, I'm
Yes,
sure it's been done.
Rob, they have, but they have come up with different conclusions. There's a group, so there's really two biomechanics groups that have gone against each other, and one suggests it's not an advantage, and the other one suggests it is an advantage, and I have not directly done work on it, so I can't say anything except that I have a very strong feeling.
There be any other last question or comments for Mike? If not, I would like to thank Mike again for sharing his work with us. So this was the last HPL seminar for this academic term, and there will be no seminar over this summer, and it'll start again in early September. Before we officially finish today, I would like to thank everyone who contributed to the seminar this year, including all professors giving me huge support, all the speakers who gave nice presentations, and especially Hoa and Stacy, who have been editing all the video files for the previous seminars and uploading them on our website so everyone can watch them. I hope all of you have a wonderful and healthy summer, and I'll see you all in the fall. Thank you so much.